Hello there. Thank you so much for joining me. Give yourself a pat on the back for doing some science on a Monday. Very good. I am Sonia and I love science. And I'm not particularly, savvy in the lab or some mathematical genius. I just kind of look around me and I wonder about things and I let my curiosity lead me down a learning pathway. So on behalf of CK-12, let's do some science, let's ask some fun questions, and travel down a learning pathway together. Alone, but together. Today, we're going to discuss magnetism. There are so many wonderful learning pathways to go down regarding magnetism. Let's first start with a big question. What makes an object magnetic? So I have three objects that I kind of just found around my house, okay? A kitchen magnet, right? A paper clip and a piece of paper, okay? Let's make some observations about these objects. So the kitchen magnet is always magnetic, right? No matter what, always magnetic. The paper clip is sometimes magnetic. So you can see it doesn't stick to the paper, but it does stick to the magnet, okay? And the paper is never magnetic, right? So it doesn't stick to the magnet or the paper clip. You agree? Okay, so there must be three types of materials then. Permanently magnetic materials, like the magnet, right? It's always magnetic. Then temporarily magnetic materials, these become magnetic in the presence of those permanent magnets, like the paper clip. And then non-magnetic materials, they never become magnetic. I hear you asking why. That's a great question. It has to do with the movement of electrons. That's right. Magnetism is very similar to electricity, which we discussed in detail last week. Check out those videos in our playlist below if you missed them, no problem. Okay, moving charges generate magnetic fields. Say it with me. That is a big idea. You ready? Moving charges generate magnetic fields. Think about that for a minute. That simple statement includes a whole lot of science. But where are the moving charges in this magnet or this paper clip? They're not plugged into the outlet, right? There's no battery source anywhere. Does that mean there are no moving charges in this piece of paper? Let's investigate further. So these materials are all made of atoms. That's right. And atoms have electrons orbiting really fast around their nucleus. That's all we need. There, those electrons moving around the nucleus, those are our moving charges. In permanent magnetic materials made of iron, nickel, or cobalt, all the teeny tiny microscopic electrons are spinning the same way and create a uniform magnetic field that we can actually observe in our gigantic macroscopic world, permanently magnetic. In temporary magnetic materials, the direction of the electron spinning are not naturally aligned, but they become aligned in the presence of a permanent magnet, becoming temporarily magnetic. In non-magnetic materials, right, their electrons are spinning, believe it or not. There are charges moving in this piece of paper, but they're not naturally aligned. They become, and even in the presence of a magnet, they would never become aligned, okay? They're kind of just spinning every which way. Want to know something super cool? Wait for it, wait for it. Okay, the entire Earth is a giant magnet. Mind blown, I know. But it comes back to our big idea. Moving charges generate magnetic fields. The Earth's inner core is solid iron and some nickel. That's right, those naturally occurring permanent magnetic materials. And the outer core is made of hot, flowing, molten metals, again, mostly iron and nickel, with tons and tons and tons and tons and tons of moving charges. These moving charges create an extremely large magnetic field. This magnetic field is very important to sustaining life here on Earth. It protects us from things like solar storms, which, yes, are as scary and harmful as they sound. So what do these invisible magnetic field lines that surround the Earth look like? Well, CK-12 has a great simulation called field lines to help us visualize the invisible magnetic field surrounding the Earth. And will even allow us to travel to other planets and explore the magnetic fields throughout our solar system. So let's check it out now. I'm going to share my screen and hop on to CK-12. All right, so here is, let me share. There we go. Okay, so here's CK-12's homepage. No place like home, right? At www, you got the shirt on, ck12.org. That's right, so you can hop on with me if you'd like. Okay, and I am going to scroll down all this great content and click on the simulations tab with that beautiful Golden Gate Bridge icon. Click there. Okay, and the sim that I'm looking for today is called field lines. Okay. So here we go. Does the Earth have a force field? Whoa. I'm going to press play. What does it mean to say there's a field surrounding a magnet or the Earth? Okay, that kind of brings a good question to mind. So does the magnetic field that surrounds the Earth, which looks like this, does that look the same as, let's say, a magnetic field surrounding my kitchen magnet? That's something to investigate. Okay, so I'm going to pause right here. Now you can see these yellow lines are what we're using to represent the invisible magnetic field lines surrounding the Earth. And you can see that these field lines extend into three-dimensional space. And we show, basically, the lines show how strong the field is in certain places. So where the density of the field is the greatest, that's where the magnetic field is the strongest. And density is just like a fancy word for like a lot of things in a small space. So you can see here, there's a lot of lines at the two poles, right? More dense. And then over here, there's less lines. So the magnetic field must be stronger at the two poles, okay? So now I'm gonna try to kind of scroll through here. Is it a force field like in the movies? That's a cool question. I think so. All right. And I'm gonna let it play through. And you can see here that this sim will let you go to different planets. There's Mars, the beautiful red planet. And also it's gonna let us move a compass around. I'll show you that in the sandbox. Because when I think of magnets, I also think about a compass. Maybe you did too. All right, now this is the image that I wanted to get to because it is just crazy. All right, I'm pausing it here. So I mentioned earlier that the Earth's magnetic field protects us from solar storms and cosmic rays. And oftentimes when there is solar wind, the magnetic field, right, that you can see there, exerts a force on these moving charged particles, and it actually pushes them into the north and south poles and causes the particles to release light. And we call these instances the auroras, right, the dancing lights. Yeah, just like in Frozen 2. So if that interests you, definitely investigate the auroras, because they have to do with magnetism and the Earth's magnetic field. Okay, so with that said, I'm gonna let you now kind of play around into the sandbox. So let's explore. I'm gonna toggle over to the simulation sandbox. And like I said before, we call it the sandbox because you're meant to kind of jump in, play around just as you would in the sandbox. And I'm going to give you some ideas for using the simulation now. So you can see you have a slider here that lets you go from different planets, Mercury, Mars, Jupiter, so on, and you actually can explore the magnetic fields there. So what I'd like you to do is see if you can figure out which planet has no magnetic field, no magnetic field. And then based on what you learned today, try to explain why that might be, okay? Then I'd like you to try to figure out which planet has the largest magnetic field, okay? I'll go back over to Earth. Which planet has the largest magnetic field? Again, based on what you know about magnetism, try to explain the reason for that planet's large magnetic field. Now, if you want to go down a different learning pathway, you can click on the compass and drag it, and you have freedom to drag the compass anywhere, okay? And I'd like you with this compass to determine where the Earth's magnetic North Pole is. I bet you will be surprised. It's not going to be where you might think. Now, there is a tutorial video that will help guide you down that learning pathway and support you with that. So if you click on tutorial up here, it's going to pop up to a 3-minute YouTube video that will help support you in understanding about the Earth's magnetic north and south poles in further detail. Okay. Now, don't forget, there's challenge questions. There's 3 of them. And I really think you guys are up for a challenge with this concept. So try to answer those. Okay. As always, don't forget, on the final screen, there are 4 more real world examples. So I'm going to click on this one. How do some birds know which direction is south? That is a cool learning pathway to go down. Many animals navigate using the Earth's magnetic field. So maybe you can figure out some other examples. One of my favorites is the blind mole rat. They're really creepy looking. So definitely investigate which animals use the Earth's magnetic field to navigate. Okay, so I'm going to stop sharing my screen. Okay. All right. So now you can see me. Have fun exploring today, and then make sure to click on the links below to the CK-12 Cafe. So earlier this morning, I posted a bunch of links to different CK-12 concepts that support many of the things that I discussed here today. And I also posted a link to the simulation and a few other interactives that CK-12 has about magnets that you can explore. Another idea is just go and grab a magnet right now off your fridge and go around your house, and you can figure out other examples of things that can become temporarily magnetic, like my paperclip. Try out a doorknob, a mirror, a pan, and then explain why this occurs to a family member. I've really found out that explaining a concept to someone really helps to understand it. So go for it. You got this. I look forward to seeing you back here again. We're going to investigate how a doorbell works next time. It involves electricity and magnets. So I hope to see you then. Thanks so much for your time today. Have a great day.